Is this thing on? What's going on? Oh, jeez. Oh, okay. We just recorded too. Okay. Alright, so hello everybody. Oh, this isn't the right page. So as some of you may be seeing, I'm trying out streaming today. YouTube's giving me some warnings about my about not receiving enough data to actually stream. So I'm also recording this on OBS, and I will upload this separately once it's done. Oh goodness. So, with all that said, as hopefully you see in the title, I'm not totally sure that the title updated. But today we're going to be working on Hartree-Fock in the Crawford Programming Projects. Okay, so if I remember correctly from when I did this for my class in Go, oops. Let's see. Yeah, if I remember correctly from before, we basically need. We need nothing from the previous project to do this. So I'm probably just going to make a new module, and it should be self-contained. What am I going to do? BRW, record style. Okay. Hopefully that should be readable now. Okay, let's find a new file. qcrab, source. I'm just going to call it HF for now. And I'm going to need to go back over here. Great. Okay, so as the description here says, the purpose of this project is to provide a deeper understanding of Hartree-Fock by demonstrating a simple, emphasis on the simple, implementation of the self-consistent field method. Okay, as I mentioned a little bit in my previous video, this is a very basic version of this kind of, I don't want to say this kind of program, I mean, because the code for the program is probably fine, but it's a simple way of handling the exact problem we're trying to solve. So the essential problem we want, I guess, in computational chemistry is typically you take a molecule, you define it using some structure. Actually, let's see, maybe this will be a fun thing to do. So WebMO is, it has like a demo server where you can run like small jobs. So I'll just show, for the people who aren't familiar, what kind of the whole process looks like. So this essentially is what computational chemistry looks like. So we'll just start with HO, just make a little water molecule. In WebMO, you can, so if we look at this, I mean, this is not a very good structure, so what we can do here, we can just mechanics optimize, then you can do what's called symmetrizing it, but those steps are not really important. So basically we start out with some structure of a molecule of interest. You plug that in to some kind of chemistry software, such as Gaussian. And the first thing you typically want to do is do a geometry optimization. So this is probably way too small to see. That's basically going to use quantum mechanics to find the optimal geometry for this molecule. So we'll get the correct, at this level of theory we're probably not going to get the correct bond lengths, but we're going to get reasonable bond lengths, reasonable bond angles, just a reasonable structure to start with. So that's kind of the first thing we want to do. You can also do a vibrational frequency calculation, but let's just start with geometry. So sure, we can go ahead and use Hartree-Fock, and we can use a minimal basis set because this is actually what the project we're going to look at today uses. So basically just run this. Is it done yet? And then we can look at the output. Hopefully we can look at the output. So you'll see the structure looks probably more reasonable now. And we can actually take a look at the raw output file somewhere. Yeah, Gaussian is cool because it spits out some fun quotes. Data viewer. Great. I don't actually use this very often. I always forget how to do it. But anyway, basically what's going on, the reason we're starting with Hartree-Fock, even though there's there's more to these calculations than just that, is that you need some kind of energy to perform your geometry optimization. So basically, we need to code Hartree-Fock so that we can code all the stuff I mentioned in the last video. Once you have some way to get the energy of a given structure, you can compute gradients for that structure, so you can optimize the geometry. You can compute Hessians, so that you can compute harmonic vibrational frequencies and stuff like that. So the first thing to do is to get some kind of energy, and Hartree-Fock is probably the easiest way to code that. So, but the limitation of this project, the main limitation of this project, is that you have to read in the integrals. So you need this integral matrix, this integral matrix, this integral matrix to actually do Hartree-Fock, well, plus the 2 electron integrals. But where do you actually get those integrals in real life? Well, you have to compute them yourself based on the position of the atoms and the basis set you're using. So in future videos, we're going to have to code some kind of representation of basis sets, because we can get basis sets from the basis set exchange. So this is where we'll get our basis sets. We'll start off with something small, like probably work on water. So we can just get the basis set. We're going to need to take that basis set, combine it with the molecular geometry, which we did actually code in the first project, and compute all these integrals ourselves. This is really the hard part. What we're going to do today is not really that hard. but it's going to help us check our work when we're doing the basis set stuff. So just giving a quick overview, the first couple steps will be pretty boring. These are just going to be reading in files. If I remember correctly, this file is a single line with a single number. Okay, so that's easy enough. Then we're going to read the AO basis overlap. This is another file. Basically, just read these, stuff them into a matrix. Same thing for this, same thing for this. Now, the two electron integrals are slightly more involved. I think they have the same form, essentially, but you have to, instead of using like a 4-dimensional array, we're going to code like this little compound index because they have 8-fold symmetry. Okay, so once all of those are ingested from the files, we can actually build these matrices. So you'll see S, L. S is our overlap matrix from up here. All we have to do is diagonalize it, or eigenfactorize it, and we'll get the eigenvectors and the eigenvalues. Yep. So yeah, we'll get LS, or the eigenvectors. Tilde is a transpose, so this is LS. Lambda is the diagonal matrix of eigenvalues, so this is just a little multiplication. This is the inverse square root, like that. And then you just start plugging into these equations. Test for convergence, and then stuff when it's converged. Okay, so that's great. And then once we have all that in place for the first example, we can double back and make sure that we can pass tests for this other stuff. Okay, great. So with that, let's go ahead and get started. Oh, I'm going to need all of these files, actually. Let's see. I might just clone the repo for this. Input H2O, H2O3G. Great. Actually, I can probably let's just copy that. All right, perfect. Maybe I'll actually stick with some TDD today. What I'm thinking about right now is how to design, what should the interface look like? So what do I want to call the function that gives us the nuclear repulsion energy? Is it going to be a method or an associated function? Probably it's going to be a method on a molecule struct. Alright, let's just write that down. To do everything here will probably but for now, I'll just make them 3 functions. Oh, I do need a molecule now. Ah, that's a good point. Alright. Let me just move this over. There's so much stuff on molecule. wish you could have multiple impl blocks. Alright, whatever. We'll just pass in the molecule. FN, nuclear repulsion. I guess it just needs a molecule. Where do I get these molecules? Molecule load. Okay, great. Hold on. Okay, this won't be used. Ooh. Okay, hold on. To eventually take a molecule out no such file or directory. That's interesting. Oh. Okay, great. Well, great, we got the nuclear repulsion energy. Check. That was part 1. Part 2, we gotta read some integrals. What is it called? s.dat. Oh my goodness. This is what it looks like. Okay. These are going to return a DMAT. Alright, come on, look. What's the deal with this? If somebody could actually tell me why this happens, I would be very happy. So you'll see down here, this function takes 2 arguments, but 0 were supplied. You put in 2 arguments. Expected 0 arguments found too. What the heck? Well, anyway, this should pass. Well, we don't have to test, so test, overlap, overlap, let's see, do they have... Okay, so actually the test will be later. So test. So that's basically how we test T and P. Let's test T and okay, so we're going to hold off on overlap intervals for now. Let T... Let's see, do we actually need T and V separately? That's the big question. And I think not. Yeah, it doesn't look like it. I think we only use those 2 for the core Hamiltonian. The B. Okay, so we'll skip overlap for now. We'll actually make a function called core Hamiltonian. Core Hamiltonian. Ah, no, that doesn't make sense. Alright. Kinetic integrals. Let E equal traction integrals. Wait, why do I have DMAT and capital DMAT? And this is what we're going to want. Okay, so yeah, we're gonna skip this for now. Alright, so there's red. Now let's make green and then we'll repack. Okay, kinetic integrals. T dot cat. Perfect. Okay. Alright, I was just taking a look at the stream health and everything. Okay, so that's what the lines look like. That's great. So as usual, we're going to line.split white space. Collect, I guess. So the first two are going to be use sizes. Okay, so the thing is, we don't know how big the matrix is until we get to the end of the file. So I probably just want to collect these into a vector. Let's see. But I don't know how to. index into the vector until the end. Interesting. 7. Let's see. Well, I guess we can just expand our matrix. I think they have this on like the user guide. Okay, so we can actually insert row. One row at the ith position. Alright, let's see. Well, we can start it out one by one, right? Whoops. And then on each iteration, I guess we can get rows, calls, shape. If I greater so when we actually index 50 I minus 1, so I think we can say if I greater than rows, actually, while I is greater than rows, ret dot insert row Oh, you moved here. What? That's kinda goofy. What? No way. Arlo. Why does checking the shape move it? It's moved here. No, that's where it's borrowed. This is where it's moved? Does this return a new matrix? Oh. I see. Okay. Okay. Well, I don't know why I just ran that. Row insertion index average. Ah, okay. I guess that's why I ran it. While j is greater than calls. Yeah. Ah, yes. I forgot about that. Okay. Seven by 7. Perfect. Okay, so instead of printing them, let's actually take I guess it doesn't really matter. Okay, we'll just set ret of I minus 1, j minus 1 to well, yeah, I'm kind of curious to see what it looks like. That looks pretty reasonable to me. One is 29. 2 1. Oh, I bet I have to copy this over. What is it called? Fill upper triangle. Let's give that a shot. Oh, right, I took out the print one. Okay, great. So those are our kinetic integrals. Oh, v dot dat. And actually we can use the exact same code. So let's just call this load symmetric matrix. So the reason to keep these separate actually is what I was describing at the beginning, is that eventually we're going to code these for real. And we're going to want them to be separate. It's only right now that the implementation is the same. Alright, great. Should I go ahead and... Well, okay, that actually means that this is done as well, right? Yep. Yeah, okay. now our overlap integrals should be good as well. Let's see if we can reformat this at all. What should we say about this? Okay, so now the next part will be a little bit more involved. The 2 electron groups. But it's not that confusing actually. The main thing we have to do is just construct these compound indices. Okay. I think before that, I'm gonna go grab some more coffee, then I'll be right back. Okay. Whoops. ERI.dat. Pub FN. So we actually just keep these in a vector. Read the 2 electron repulsion integrals from the ERA.dat file. The integrals are provided in Mulliken notation over real AO basis functions. The integrals obey 8-fold permutational symmetry relationships. Okay. Yeah, stored in a one-dimensional array. And I actually have a slight improvement on this storage, but I'm not going to test that out until I know that the rest of it works. That will be a refactor thing, for sure. Okay. U is greater than nu, lambda is greater than sigma, and mu nu greater than lambda sigma. Okay, so basically we need a helper function for this. I'm just going to call it index. Something we could consider doing here is actually, let's see, consider yeah, actually, let's do that, because we can actually implement index. Okay, let's actually make a type. This is going to return. Let's just make this return an ERI. In which case, this is just going to be called new. It's going to return a cell. Let's see, are we going to be able to do this? We have to do it in 2 passes. How did I do this before? Loaded mat, yep. Yeah, there's index, mu lambda sigma. Load ERI. Oh, that's right, that's right, that's right. You don't need to know the number up front for this one because you can just append it. Alright. Okay. Let's do this. Whoops. Struct ERI. Oh, right. Index. We'll just make it a U size, U size, U size, U size. Great. And this is where we can actually, this is beautiful. This is beautiful. I quite like this. Okay. Let ret equal vec new. What's it called? Inner. Okay. So I can use most of the same structure from this. We don't need all of this. Okay, great. Okay, line F dot flat. Oh yeah, I think I usually call this lines, right? Split. This time we want it to be equal to 5. Let's see, so we're going to need some way to compute the index. We can do a little helper function, right? Well, let's just do it like this. U, nu, lambda, sigma. So that's great. So yeah, we're gonna. This is basically going to call self.inner of index okay, and the way it's going to do that is as described up here. Mu greater than or equal to nu, lambda greater than or equal to sigma. Alright. Let mu m equal m. No, these don't actually have to be equal. Let m equal well, okay. So basically we're going to make mutable copies of these. Okay. If m less than n, oh, I see, I can just do this. Let mn equal, if m is less than n, we need to swap them. Else mn. I can delete that. And I can do that. That satisfies that. Okay. Mu has to be greater than or equal. So if m is less than n, swap them. Okay. Same thing with lambda and sigma. Okay, so now we compute mu nu and lambda sigma. Alright, let me just try to remember. I think this only works if the indices start at 1. This, you guys may have caught when I was looking at my Git repo. There's a file called, like, tricks. And that's why I wrote down stuff like this. Maybe this does work fine if they start at... This looks like it's okay if the indices start at, if indices start at 1 or 0. And then I have to do this check one more time. Mu nu. that way we, I'm just drawing it out a little bit so we don't have to repeat ourselves. And then basically let MNLS equal, let MNLS equal compare MNLS. And then finally, what we return is compound of MNLS. Okay, so two, three, and this is 4. Let's see what this looks like. So it should go up to 406. I'm pretty sure I remember that. Oh, great. It didn't run at all. Where does this actually get used? So the other thing is we don't use this for a while, and we don't use this for a while. Okay. So I guess I'm just gonna have to. Alright, it will get used when we do the new Fock matrix. What? What was that? Go 3G/ERI.dat. So let's run that. I just want to see the indices come out. So I remember they go up to 665. That doesn't seem right. I remember them going up to 406. Load ERI. I thought I had an insertion somewhere actually. Maybe it was 665. I was pretty sure it was 406. Okay. Maybe this is right. So the reason I brought up some improvements that we'll try to do are that you can see that this is a pretty sparse array. Oh, maybe there are only 400. No, that doesn't make sense. Huh. Let's see. I don't really want to run the Go version. I don't even have this on my computer. I could have sworn I had. No, that's the only place I even call it. I thought there were 406. I guess I could have made that up. What? Oh. it's kind of large. Basically, I just want to make sure that my electron repulsion integral vector is correct. Project 3. What's in this big file? Oh goodness. Go test. So I want to test Fock. I'm trying to remember how you do this. Test Fock. Go test. Oh, it's just dash, right? Okay. $406. Okay, so I did mess with it. What I messed up is I need to subtract 1, actually, from each of these. That's what I was just talking about, too. Yeah, 405, 406. And then, wait, am I supposed to subtract 1 from the resulting index as well? Index plus LS. No, it looks like I don't have to subtract 1 from that. Ah, yes, so it starts at 0. Perfect. Okay, great. Alright. See if that works. If index greater than, oh, right. So we make the length at least 1. Okay. Debug inner.length. So it says 406. Excellent. Okay, so I think we have loaded great. So now we can actually index our ERI later just with a tuple. We don't have to worry about doing this indexing or anything like that. Pretty sweet. Okay, so I think we just loaded the 2 electron integrals. And we're already up to step 6, building the orthogonalization matrix. long have I been going? Oh, an hour, nice. Okay. Now we're going to build the orthogonalization matrix. Here. Oh, right. My god, that is so annoying. Oh, man. I definitely missed the nice formatter in Go. It handles all that formatting. Okay, so we've got all of this stuff loads in. Yep. Now we need the orthog matrix. Build orthog matrix. So it needs to take S. Is this the only place you use S? In that case, you know, you may not even call S directly. This looks like it takes. Well, we'll pass it in. It's fine. Diagonalize the overlap matrix. Build orthog matrix. It needs to take S, which is a DNet, and it's going to return a new matrix. I need the eigenvectors. lambda f is the diagonal matrix with eigenvalues. Okay, so I need to make a... Actually, why did I close my code again? So, alright, when you see minus 1/2, does that mean that it's the diagonal matrix taken as where the diagonal is set to 1 over the square root of the eigenvalues? Maybe it's the same, actually. Or is it like the matrix inverse of the square roots? I think it's probably the first one. Dense 2 sim. Goodness. S12. Vectorize. So we're just setting the diagonal 1 over the square root. Yeah, okay. So that's what it is. So I probably need to sort these again, right? Like, you'll notice in the documentation the eigenvalues are the unsorted eigenvalues of the decomposed matrix. And I'm pretty sure they're supposed to be in, like, descending order or something. Ascending order? Yeah, like, if I do this now, it's just going to be random. I'll just return LS. Build orthog matrix. Yeah, see, like, they're just a random order. Okay. So I'm gonna have to use what I did before in the rotational constants, where you have to, like, sort these. Oh, do we not sort them? Ah, okay, no, this is one of my other programs. I might just copy it over. I don't really want to write it again. It wasn't that hard. Let's see if I can find it. Oh, it might actually be in my symmetry package. Where was I doing this? Trying to sort it by the eigenvalues. I just wish that they came out that way, you know? Oh my goodness. I know I did this the other day. I just can't remember. I thought it was in the symmetry thing. Principal moments, principal. Oh, it's right here. Right here. Yeah. Eigenvectors, eigenvalues. Yes. Okay, so Vex. Okay, so this section here, sort the eigenvalues and then the eigenvectors correspond. So we do that now. Hopefully it's going to be in the right column. Ouch. Unable to copy from a matrix with a different shape. Oh. Whoopsie. What? Well, that's interesting. It's S12. Well, that's strange. I think. Maybe I should just try doing the math and actually see what happens. Maybe it's not a problem at all. Yeah, I guess maybe it's not. Okay. So LS, you can make like a diagonal matrix somehow. Set diagonal. Content of the vector. Beautiful. Okay. Here I can let lambda equal dmat zeros RC lambda dot set oh, wait. What? No, it told me that set diagonal takes a vector. Oh. Ugh. Alright, so that's going to set lambda L minus 1, 2. Okay, so now I take LS times lambda times LS dot transpose. See what that looks like. That does not look quite right. That doesn't look right at all. LS is the matrix of eigenvectors. Well, it looks kind of qualitatively right. That's good. Wonder if the problem... Alright, we got a couple chats. Hey, how's it going? Yeah, this is just some chemistry stuff. I guess I could send a link to these programming projects if people are curious. I'm not sure that will exactly answer what this is, but at least kind of. Let's see. I'm doing pretty well. I'm having fun programming. What's better than that? And I'm doing even better now that you guys are here. Let's see. Now if I can just figure out what I'm doing wrong, everything will be good. Let's try not sorting them. It doesn't make sense not to sort them. Oh, wow, okay. Oh, duh. Okay. mess that up. Oh, is that the right answer? Okay. Well, I guess I was overthinking it again. Great. What's Emacs for writers? That sounds familiar, but I can't remember what it is off the top of my head. Oh, I forgot to do anything. Let and I forgot to actually return the right thing. Alright, it passed. 7. Ah, maybe I have seen that. Yes, speaking of that though, I've been thinking about doing a video of me just like writing LaTeX. So some of the chemistry programs we use, well, not really chemistry programs, I guess. They're kind of in need of a new manual. Like there's one written, but it would be nice if I transcribed it. So I may have a video of me just writing LaTeX pretty soon. I think my LaTeX videos seem to get the most views, so maybe there's a big audience for that. Great, so we got the orthogonalization matrix. No, I'm using DWM. Yeah, I started out using i3 as my first tiling window manager, but pretty quickly moved to DWM. Just mostly because I like the automatic tiling, like how it just does that kind of thing. I got kind of tired of like moving the splits around in i3. Oh, it's no problem with the thought process. I mean, I'm doing this live stream to talk to people, really. That seems a little more fun than just like recording the video, posting it, and then people hearing back from people like weeks later. Okay, I'm gonna leave this for now because I have a bad feeling that this comes up in the larger molecules. I think maybe it matters more then. Okay. So build the initial guess density. Only the occupied modes. I guess I can delete it. Because we can always get it back from Git. Let's build the initial guess density. So I'm trying to remember how this works. So we form an initial guess of our Fock matrix using the core Hamiltonian. So I guess we pass in Fock, S. Okay, that's all we need, I think. Fock and S. SCF energy. I remember having some difficulty, some like disagreement with myself with how to structure this code in the past, so hopefully I can find something good this time. But as I usually do, I'll probably just start writing it and see how it goes. So what we got, it's going to be density of, so we have to give it an initial Fock matrix, which is actually H core in this case. Let's give it Fock, and we have to give it our orthog matrix. So I'll just call it S12. S12. So our Fock is our H core. So where's my test H core? And then I can actually inline both of these. Kinetic plus subtraction. So there's Fock. And then let S equal overlap integrals of S. And then let S12 equal build orthog of S. And now I just need to write the density function. And it's going to return the density matrix. So we take the Fock matrix, S12 transpose times Fock times S12. And sure, I can just return that for now. think did I write a macro for this? Oh, I did. Not a macro, a struct matrix. Alright, that looks great. Initial MO coefficients. So now I diagonalize it, transform the vectors. Initial MO coefficients 3. Okay, so I need to multiply that by S12. No. Oh, you switched to computer science? So I actually very nearly did the same thing. I started out in engineering, and I dropped my first chemistry class actually because I missed some assignments in the lab, and I was like, oh, I'm not doing this. I dropped chemistry. The next semester I tried computer science and didn't like it either. And yeah, I really love computer science now. I hated my first Java class I took. So I couldn't really get into it in college, but now that I do it in research, I love it. But yeah, chemistry originally was really tough for me as well. I had to get a really, really good professor, and that's when things kind of started to click. Okay, this doesn't look right. Oh, now the columns are in a different order. Does it matter? I think it doesn't matter. Yeah, I think this is where I realized that the coefficients can be in different orders. And it doesn't matter because you're doing this. Okay. So in the density matrix, you actually have to tell it how many electrons there are. Yeah, dense is the number of electrons. Well, oh, and this way you use the geom file for it. Ah, that's right, that's right, that's right. It's the charge, of course. Oh, that's cool. Yeah, I think Python. I think with Python I would have been a lot more hooked. The Java stuff we were doing just killed me, and in that case it wasn't even. I kind of feel like the class was like too easy, because all of our assignments they would give us a program that was mostly done, and we just had to fill in a tiny bit. So basically I made it through the class with learning like no Java, and I never got hooked on programming because like I'm just doing these little tweaks to stuff that already basically works. Yeah, I think I took a Python class later that was a lot more useful, even though by then I kind of knew Python a little bit already. But yeah, so I'm in grad school, just wrapping up my third year, and I'm in a chemistry department, but I do computational chemistry, so a lot of the stuff is kind of like a mix of computer science and chemistry, really. I think we have something called weights, right? Some self.atoms.iter. I guess we need iter map. Is that what? Oh, in this. Oh my goodness. Ten electrons. Yeah, that's right. And sorry for any delay answering questions. I didn't realize how much stream delay there is. Maybe, I'm not sure how perceptible it is on the viewing end. But for me, like, I can see in the little preview on the side, I think I'm like minutes behind, potentially. I think this is wrong. So if all the electrons are paired, let's see, if I had 9 electrons, yeah, 9 over 2, it would give me 4. So I'd be missing the unpaired orbital. So I've got this. Now I just need to build the density matrix. And it's going to be let mut ret equal Emat. Yeah, nice to meet you, man. Is this molecular rust? I guess so, yeah. You knew. So this is something maybe mildly interesting to point out, but basically, if you count the subscripts you see in these equations, that's how many loops you need to have. So D, I'm building a matrix called D that has dimensions whatever mu and nu loop over. And then we'll have another one for M. Using the occupied MOs. Let's see. Now are they M indexes? The summation includes only the occupied spatial MOs. Well, we can actually see this from the hint. How big is it? It's still 7 by 7. So mu and nu are looping over all of the orbitals. So we got 4 mu in 0 rows, mu in 0 falls. Of course, those should be the same because everything should be square and symmetric, but or maybe not symmetric, but certainly square. And then we can play. At some point, I want to do some profiling on this. To see, because we can always try like interchanging these loops. Okay, so ret of mu nu plus equals, what did I call? Oh. C0 of mu m times C0 of mu m. I forgot one of them. Oh, that's my bad. Okay, did I actually write the test? Okay, no I didn't. Okay, I totally didn't believe that. Alright, let's see if it actually passes. Okay, it actually passes, supposedly. Does it fail now? Okay, why is this? Something's wrong. Oh no, does that mean all of my tests are wrong? Yeah, this is not right. Why is this test passing? This is not right at all. Oh no. MX brown. I think these are MX reds. Let's see, I have a red dragon. Let's see. Just like the cheap one on Amazon. I think it's this one. Okay. Yeah, K552. Yeah, this is the one I have. Except mine is just, mine doesn't actually have the RGB, it's just red. And yeah, I think I have the one with the red switches, not the browns. Why did I learn Go? Basically, I was starting to work on a research project, and I tried writing it in Python, and I also tried writing it in Julia, and I kept hitting so many like dumb errors from my side that that something with static typing was really appealing to me. And at that time I also considered Rust, but just looking at Rust code, I found it really off-putting. Like all the brackets and stuff, I really didn't like. So I went with Go. And I also thought that the Go's concurrency stuff was really appealing. I ended up not even really using it in my 3, 4, 5, 6. I ended up not even really using the concurrency stuff. Well, I tried to use it at the beginning, and it was actually not a good idea. So that was one of the other reasons I went with Go. But I quite liked Go. I mean, the tooling is really nice as well. I still think the tooling is slightly nicer most of the time than Rust's. So I have no idea why this test is passing, which is kind of a scary thing to say. Because that matrix is not right. But yeah, so the Go stuff is still really nice. I kind of prefer how Go does tests. But I already really appreciate all the stuff that the Rust compiler does for me. It checks a lot more stuff than the Go compiler, and I feel a lot safer with my Rust code. Yeah, so I'm probably, sometimes I still write a little bit of Go on some old projects that I try to keep maintaining, and I'm always missing Rust the whole time I'm doing it. So I liked Go when I was using it, but I definitely prefer Rust now. Okay, so I'm going to have to think about this a little more, unfortunately. I'm just closing this. So I can check the Fock matrix, I can check the coefficients. I think the Fock matrix is okay. Well, that was very strange. Okay. Okay. Fock looks like this: 2, 5, 4, 5, 8, 6, 6, 7, 9, 1, 4, 9, 0. That's close enough, I think. Good. Okay, this is all looking fine. Okay, that looks good. Now the coefficient matrix. I could make these like separate tests. I'm hoping to avoid that, which is why I'm doing this kind of silly comparison. Okay, now this part looks wrong. Coefficients are not even in a different order. They're just wrong, I think. Because I don't even have one that looks like this. This, I guess, is the closest one. That's different. No, okay. I think something's wrong with my coefficients. Which is kind of strange. Did I do them? Coefficients. These are the orbital energies. These are the eigenvectors. Eigenvectors. S12 times C0 prime. I know I'm kind of cheating looking back at this, but it keeps this from being like an all-day kind of stream. I wish they gave us the orbital energies. It might be in the output, actually. Let's take a look. Initial Fock matrix, initial coefficient matrix, initial density matrix. No, I don't get the orbital energies. My S matrix is correct. I thought I just tested that. Good orthog matrix, overlap labels. Well, I guess I can print this one real quick. Okay, so this is my S10236. And this is actually tested. I'm not sure how it could not be working. this is the kind of debugging I cut out of the last video, but I guess on a live stream, everybody's stuck with it. Okay, so my S matrix looks fine. My Fock matrix looked fine as well. Oh, I'm printing the wrong thing. Oh my goodness. Okay, hold on. C0, okay, wow. Wow, that's good. I was just printing the wrong thing. Is it right? 1.5. Okay, so now they're just in a different order, which should actually be okay. I think that's okay. Maybe it's not okay. I think here maybe is where I have to sort them. Okay, let's go back to the last commit and grab this code. Okay, I guess this is where it matters, because you need to sort the occupied ones lower. Oops. Take this out. Uncomment. Okay. I'm using DWM. Oh, it's one of the suckless programs. So it's an auto tiler, is that what it's called? Dynamic tiler? I guess it's kind of hard to tell actually, because most of what I do on the video is in Emacs, but it does tile like that. Yeah, like I was telling the other guy, I did start out with i3, but I got kind of tired of like having to manually tile, like move the window arrangements around, so I switched over to DWM. Okay, I need to hold off on that part until they get sorted. So we got sim. Yeah, I really like DWM. It's really customizable. I actually have, let's see, yeah, GitHub. I have a lot of my config files. Not really my full config files, but this is like my build of DWM. So I have a couple patches added. So I have like the systrate thing added, for example. You can see the OBS and sound stuff up here. And then I also have the swallowing patch that basically, if I open like a PDF or something, it, like, the terminal eats it, basically swallows it, I guess is what they say. Yeah, so it's really configurable. Where is it? Config.h. You just add all your key bindings and stuff. I really like it. I can't really imagine using anything else. Diagonalize it. So this is actually going to be C0P. Yeah, it's super convenient. I mean, it's slightly not convenient that it's written that the config file's in C and you have to like recompile it, but it's really fast to recompile. And once now that I have been using it for a long time, I don't change it that often, so it doesn't really bother me. I don't understand why this is... moving it. I shouldn't have to clone it to do this, right? Oh, I see. My goodness. Alright, fine. Okay, so this is this right now? This is the density. Is that what it's supposed to look like? Yeah. Oh, I was printing the wrong thing. Is that right? Okay, so my density matrix, or my coefficient matrix still looks wrong. It's wrong. Oh wow. Oh wow. Yeah, that really doesn't look right. Oh. Wow. Okay, yes. Oh, okay, there we go. Yes. So I think I did have to sort them. Now, why does my test pass anyway? Okay, that doesn't make any sense at all. Oh, I forgot the assert. What? Oh my goodness. Wow, why is there a macro like that? Okay, we got the density matrix. This time we did actually have to sort them. Now that we have the density matrix, we can compute the initial SCF range. This is great. This is just a number. Beautiful. Okay. We pass in the density. Test. SCF init. Okay. I actually need most of this stuff. Okay, we got the molecule. Let D be this, density. So now what I can do is sum over all of this. Sum over mu nu. Alright. D times H core plus H core. Probably have to clone the first one. Okay. 2.0. That's one other thing I missed from Go. Is that you can just write 2 and it'll like infer the type. I wrote something else down in my tricks file. Step 5. Operations are element-wise. I kind of doubt that. I guess it could be true. Hey, how's it going? Yeah, so I was afraid that my internet was too bad to stream before. And I didn't do anything, but I checked the upload speed again and it seemed okay. I've been watching out of the corner of my eye on the other monitor. The connection health is sometimes it's not good. I've been getting some warnings, but I think for the most part it's acceptable. So yeah, I'll probably start streaming. It's good to actually get to talk to people, you know. Alright, let's get this electronic image. So I wrote down that these have to be element-wise. I don't really see why that's the case. Oh, thanks. The stream quality looks good. That's I should have asked when other people were joining. Thank you very much for telling me that. I actually had no idea. I was just hoping. Okay, maybe it is element-wise. So let's take D ij times each core oh, whoops. How does that look? Oh, this must be the electronic energy. Okay, so I can actually leave out the nuclear repulsion. And let's see, it agrees to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. Okay, great, we got the SCF energy. Compute the new Fock matrix. Oh, goodness. Okay. So we've actually already taken care of step 8. This is the same as step 5. It's just that you call the density function with f instead of each core. The new Fock matrix, so we'll call that function Fock. And then I guess I actually need to make this an energy. So it's going to take the density, it takes each core and the Fock matrix. No, please. I'll just do it myself. So that was, I tried using the extract function thing, but it didn't work pretty well. Fn, SCF, energy. Maybe we'll just call it energy because it'll be in the HF module. So, yeah, it's going to be interesting actually working on the API for this later. Okay, so the energy, if we go back here, we need the density. Why did that happen? Okay, I don't know what's going on. Okay, so I need the density. And don't forget to change this to Fock, because later it will not be H-core. I really wish I could do this. Oh, I guess it kind of worked. Well, shit. Compute SCF. Okay, so that's the SCF energy. The next thing is just to update the Fock matrix. Building a new Fock matrix. I feel like you pass... Do you pass the last Fock matrix? No, I guess you just use the previous iteration's density. The double sum runs over the AOs. Fock build code. Is this the tricky part? No, that's not too tricky. Alright, this is where we actually get to use our indexing stuff. Not forget the assert this time. So to update the Fock matrix, we need H-core, density, and ERF. Say D, H-core, and ERF. So I've got D, and all of this, and then I also need ERF. Okay, I need a function called Fock. This one, maybe this isn't, this may not need to be pub actually. So I think it takes the density, dmat, H-core, dmat, and ERF. It's going to return a new matrix. So it's going to have the same dimensions as H-core. Sandwich all of our code in here. What's the matter? Can't. Oh. Fock matrix. Okay. So I think actually you can actually initialize Fock to H core, and then we're just going to add to it as we loop. So we got mu nu lambda sigma for loop over AOs, and I guess we can even look at this, right? Yeah, all the loops are over the same stuff. So we can actually insert EQ RC. M in lambda sigma. Or lambda sigma. Alright, so the sum over lambda sigma. Well, it doesn't really matter. Okay, so we'll say Fock of Mn plus equals D, density of lambda sigma times 2 times ERI of mu nu lambda sigma minus ERI of mu lambda nu sigma. And this 2, of course, is going to float. We'll see if it works. And supposedly it worked. At assert abs diff EQ. For anyone not watching earlier, I forgot the assert part before, which doesn't work as well. Just change another random number. Okay. I think changing the last one doesn't seem to work. Oh, it worked that time. Okay, so I think we got our new Fock matrix. Yes, and I actually considered using the Greek symbols in here, and I decided against it because it's slightly inconvenient. You can do, so yeah, I just hit control \, and I can actually change my input method to LaTeX. So I can write mu nu lambda sigma. And I think you can actually do it another way. You can do like control 8 enter. Oops. At least I thought you could do it like that. Is it not that? Maybe I have to change my input. Control 8 enter. Oh. Oh, maybe they. Oh, did they take that back out? Let's see. Insert Control X 8. Control X. Oh, 8 enter, of course. Yeah, yeah. You can also do it like that. Greek new. Letter new. Like that. But I usually do the LaTeX input method. And I think Rust does allow this. But as you can see, it gets kind of annoying, I guess. I should make sure it does recognize it. Yeah. And I'm not sure I could do... Could I do this? I don't think I can toggle my input mode in a replace. Yeah, so I think Rust will allow this, which is pretty sweet. I mean, on an aesthetic level, I do prefer that. I just thought that practically it would be kind of annoying to type them. What is it? That's interesting. Yeah, but this is in other contexts. This is really cool. So I use this mostly in documentation. Because then I don't really mind typing it. You can also use like sub and superscripts. It's great. So I can do like D, mu. Oh, it doesn't work. That's right. You can do like D. If you have regular, those are really small too. But I definitely use this for documentation. I love it for that. And I love the way this looks. This is great. It's just practically, I thought it'd be annoying to type. But yeah, that's a cool trick that I didn't even know about until pretty recently. Keep the updated Fock matrix. Alright, so I think the only thing we have left to do is this. Iterate and test for convergence. So, basically, Hartree-Fock is just this. It's density Fock matrix on loop. You just go back and forth. You get a new density, new Fock matrix, new density, new Fock matrix, until self-consistency is achieved. So, of course, that's where self-consistent field comes from. Now where to do that is a good question. I guess I'll make it, what is this energy? I don't know, I might call it like do SCF or something for now. Oh yes. Yeah, there's another annoying thing in Rust, is that if you forget to toggle your input method back, it's going to eat all your underscores. Okay, so we're going to do SCF, and what you need to do SCF is pretty much everything, I guess. I guess we don't really need to do clear repulsion. I don't really care about that. I guess I need T, I need V, DMAT, I guess these can all be references. T, V, DMAT. So we're going to assemble our core Hamiltonian with that. I think in the Go version I have something called like work, where, oops, project 3, no, I guess not. Let's just go through the test and see what I have to do. So we need T and V. We do need ERI. Oh, I guess I can delete this. We have to do this. Yeah, basically I can just go here. We have to pass it T and V to build H core. Wait, I think actually we can just pass it H core if we want. Yeah, this probably just needs H core. It also needs S12, and it needs the number of electrons. Is that how we want to do this? I guess what I'm considering right now is how many of these things are useful for other methods. Because if they are all specific to doing SCF, then we can just compute them inside of do SCF. But if the data structures or the things are going to be shared by other methods, we may want to compute them outside and pass them in. I guess I'll go ahead and just pass in this stuff I need over here. So S12 is a DMAT, ERI is an ERI, and I think that's all we need. And what is the product of our SCF procedure? I guess the product is like the well, I guess for now, I'm probably gonna skip this stuff for now. Oh, we want the final energy is basically what we want. The final electronic energy. So I'm just gonna have this return a flow 64. Eventually, we're probably going to want the Hartree-Fock orbitals and stuff like that, but that'll be... A lot of this stuff will become clear when you actually try to use it. It's like, okay, I want to rework the API so it's not as painful to use. Run the SCF procedure to return the final energy. That's pretty much all I know about it for now. Do SCF. Okay, this is going to be pub. I just need to make this pub. It's fine. It's not a big deal. Why? Okay, there we go. 0.0. Yeah, I'll print that stuff. Why not? So the first part... Oh, this does also need a molecule, actually. Okay, so, no, it doesn't, does it need that or not? Really, it just needs the let use on. Okay, so, the initial, let's go back through the steps a little bit. Compute the initial SCF energy. So we need the initial guess density. So I'll go and call this D0. And this is just going to be nalec. Compute the initial guess density. Okay. Compute the initial SCF here. We don't actually use that. I guess we're gonna want SCF init. SCF init. D0. Compute the new Fock matrix. Let Fock. So this is going to change, so we'll just make it mute. And let's make this just D. I'll make it mutable as well. Let Fock be Fock. Yeah, I need to borrow all of these. So that's going to be my new Fock matrix. And then I think we just start looping, right? Let's just return SCF init real quick. And let me make a quick test for this. Yeah, what I'm trying to do is just put all of these down at once. But you see that it only does it. Does that. Do SCF. Yeah, naming things is one of the hardest. It's one of the hardest things, right? I don't need the density this time. Alright. Let God equal do SCF H core S12 ERI mol dot in elect. And then I need to borrow everything. I don't want to borrow that. Okay. And then I'm just going to copy how they spit the stuff out. Iteration by iteration, electronic and total energies. So we're going to be printing these 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 21.12. Or, yeah, so 21.12. Let's go up here. Print line. I think there's a way in Rust to use the same format for multiple things, but I'll just do it like 1, 2, 3, 4. We are going to print. Let's go do this. Iter. Let's just call this energy. This is going to be mute as well. I'm actually going to skip the total energy. I don't really care about that. The delta E and RMSD. Okay. So let's see, we got initial density, initial energy, and the initial Fock matrix. For iter and 0 to 1, let's do this. So that gives me iter. Let delta E equal energy minus 0. Let RMSD, what is RMSD? I might just lift this from one of my square this. Look. Alright, we'll just write it ourselves. Yes. So this, what I'm working on right now, is in fact for water. The first test case is stow 3G water. So, yeah, we're basically working on the wave function of water. But hopefully, if I've done everything correctly, we'll be able to just plug in the stuff for methane as well. don't know why they write RMSD like that. And I always want to lead with the new line. And let's go ahead. So the iter left align, center line. It's pretty cool that you can center line like this. So, I mean, they skipped the delta E for the first one, but great. Okay. This minus this, square the differences, add them all up, take the square root. Okay, so now basically I need to maintain not just the current values, but we need like the last value. So at the end of the iteration, let mu d and then we can then you get the new density, the new Fock matrix. Let mut Fock equals qcrab to start. And the density matrix is actually made with the Fock matrix, so this should actually be Fock. Okay, that's pretty annoying as well. Yeah, that's a good question. So, Hartree-Fock is one of the cheapest methods for doing this, so it doesn't take that long. But of course, I mean, good approximation is the kind of operative term there. So Hartree-Fock is not that expensive, but it's one of the most basic, and it's not very accurate. Do we have theoretical values for the wave function? Kind of. I mean, there are higher levels of theory you can use. So actually, let's see. In these programming projects, basically as it goes, it gets higher level. So Hartree-Fock is kind of the basic thing that other things are built on. So if you go to project 4 and you do the MP2 energy, that's going to give you a better, at least a better energy. And then you can go up to a couple of cluster theory, which gives you even better, more accurate energies. Although some of these don't actually give you a new wave function. I think probably all of the perturbative ones... I'm trying not to embarrass myself. I can't remember. Some of them don't give you actual new wave functions. They just give you better energies derived from them. I think that these do actually give you wave functions back though. So these two, this one would probably give you the best wave function. Once you're doing this perturbative triples correction for CCSD parentheses T, these are kind of the gold standard for energy values you can get, but this one definitely doesn't give you a new wave function compared to CCSD. So, this stuff, what we're doing here is not very accurate, but it's also not that expensive. I'm hoping when I run all of these test cases, they'll be able to finish in like, you know, a minute. Faster would be better, and I might do a little profiling to try to get to that point, but we'll see how it goes. I think in the Go version, it could run all the test cases in about a minute, but when I wrote the same thing in Python, it would take like, maybe not for Hartree-Fock, maybe that one wasn't as bad. But in one of the later ones, the running in Python was just, it would take like 10 minutes, 15 minutes. Let's just call this F, I guess. Okay, is that the right first energy? 842.07743.7699. Great. So let's just make max iter like 5. So I mean, you'll see that this procedure is going to converge after like 34 iterations. That doesn't mean, so that's that means that this energy is like as good as it gets for this molecule and this basis set. It doesn't mean that that's like the that that's really exact. Oh, I forgot to update anything. And this is now just F. Okay, how does this work? Okay, great, it's not right. 842.077.4. So the first one is still right, the second one is not right. And I have to try to remember why that is. I think it's because let's see. This is kind of a touchy thing because some things you have to do outside the loop, but then you also want to do them in the loop. Okay, very first thing we do, we build the initial guess density. Let's try doing this in the loop. I've actually never used C++, so I can't really say if I like it or not, but after using Rust, I'm going to assume I would not like it, because I expect it to feel like when I go back to Go, but possibly even worse, where I'm like really scared that the compiler is not catching stuff for me. That's a good point. I don't think I'm familiar enough with the NumPy and the SciPy stuff to make it run fast. I did a little bit of profiling, but I think I couldn't make it any faster using a lot of normal Python stuff. If I used the appropriate NumPy and SciPy stuff, I think it would run a lot faster. So that's mostly my fault. So we're going to take the guess density. Oh, this is supposed to be Fock as well. F. Okay, this is Fock. We get the density, we get the energy. we use the density to get the new Fock matrix. F starts out here. D is this. So see, in Go, what I would do is just say like var D, there's a D mat. And then that will let me set it the first time I go through. I guess I can set it out here though, right? Oh, but I don't, okay. There's this. Let me use D. So we're gonna use D, we use H core, we use F. We use F. Okay, the energy we actually don't. No, we need energy old. Okay, no, this is fine. Energy old is 0. And I'll change this to E old. E old. We do need D old. Okay, that can go here. E. Let E be this. Okay, so delta E. This is E old equals E. E minus E old. Okay. Cannot find value E. Yes. E old equals E, so we'll just return E old. Now is that right? 842 07743 7699 7828658 3284740. That actually looks right. 7198. Okay, that looks great. Yep, 47 5.7. All right, now if I just do the RMSD, I think we'll be good to go. Yeah, so I think my Go and Rust versions are not squeezing all the performance out either. In the Rust version, I would like to try to do that. The Go version was like surprisingly fast. I think mostly because the GoNum libraries seem really fast. I would love for the Rust version to be faster. So we'll see how that goes. I really like profiling. It's just like the first pass I do. So the last time I was writing this, the Go version and the Python version was for a class. So I was kind of like constrained on time. And I was doing the Python version mostly because my classmates were writing it in Python. And so to help them with their versions better, I was trying to do it myself in Python. So I wasn't like super focused on getting it that fast as well. Yeah. So new minus old. I wonder, can you do an element-wise? How I. Ooh. Raise this matrix to an integral power. Beautiful. So we're gonna square it. And sum it. Sum dot square root. And I can even inline. Oh, beautiful. A one-liner. That shot. Did I mess this up? I don't think so. My RMSD just doesn't look right. Take the difference. Alright, yeah, you have a good day too. Thanks for coming by. I wonder if I've got... I'm doing something backwards. I think I might need to do this. So square the difference, add it up. Oh, I forgot to take the mean. Whoops. That's right, that's right. Let's try that. Uh-oh. Root mean squared. Why is that not right? Isn't that the number? It's the mean. Wait, what do they divide by? Well, I know in my version I did the... Oh, I actually do the norm. Not the matrix norm. There we go. Okay, 8266. Yeah. Alright, great. And now the test for convergence. Yeah, delta 1, delta 2. So those are the convergence criteria. Okay. So we'll just ensure that they're larger, right? So now, while dE greater than d1 or d minus d we'll do this. And I need to actually update DRMSD. Actually, call it R. Well, I guess I can call it RMSD old. No, R old. Oh, is this supposed to be the delta? No, just RMSD. Oh, right. Let's see. What do they set their convergence criteria to? So I'm going to say 1e minus 12. See how it goes. What? Oh, right. There we go, 35 iterations. Beautiful. Alright, and the final energy I want is this. Okay, I think that's going to be it for today. I know there's some... Oh, I should do the other test cases. What? Okay. Okay, I should do the other test cases. I'm going to skip this stuff for now, though. The additional concepts. So, we'll need this fog matrix for MP2. But that stuff's way down the road. Like I was mentioning in the beginning, I'm going to stop saying this over and over eventually. But, like I was saying at the beginning, now that I have Hartree-Fock working, I'm going to be focusing on computing the integrals myself instead of moving on to the other programming projects. So the other programming projects are like way down the line. Maybe I'll come back to them. It kind of just depends how much work it takes to get the integrals, and then probably even stuff like geometry optimization is working. So not worried about this last part for now. Yeah, I don't think I'm worried about any of this stuff. Population analysis. What I am going to do, though, is try to do these other test cases. So, iterate and get the final SCF energy. Let's see. So, let's start. The hope here is that I can just run the do SCF test, and that's going to cover everything. But if this starts going wrong, I might have to like propagate the test back up the stack, basically. Okay, let's see what we can do. So I'm going to try to give this just a direct read. We'll just call it 1, 64. This doesn't need to be the back, actually. You gotta put 2 in here so the formatting doesn't mess up. Ugh. Does that work? No. No. Found path buff. Can I do something like this? Does that work? P as ref path. Okay. great. Just barely fits. Fantastic. Okay, this isn't actually so bad. Oh no. Okay, well that was a little bit scary. For no reason, apparently. Okay, so what I want to do now, CP temp programming projects, project 3, input, H2O, okay, so now I've got DZ, and the value I want from that is this. Yeah, let's see if that works. Okay, it worked. 9802460371887. Okay. Well, that's very exciting. DZP. Maybe this shouldn't be so unexpected, but pretty exciting. See if DZP works. Oh, right. Oh, okay. Anticlimactic. Yeah, so you can see noticeably, right, that these are actually slower to run. Basically what's going on is that the number of integrals is increasing because these basis sets are larger. Yeah, okay, that worked as well. 0111888547111. And you can see that actually if we just take a look at DZP, for example. So these go, we're only 2% of the way into the file. So this is like kind of a gigantic file, 30,000 lines. Because we now have 26 basis functions, I guess, instead of 7 in STO3G. Yeah. So that kind of explains that. The last test is guess I just want this here, right? Okay. The last test is methane. So this basically tests if anything we did was specific to water. Oh wait, where are the energies? Oh, right. Like if I hard-coded a 3 somewhere, something worked, oh man, maybe I changed it before it actually loaded it. Yes, you can see how long this actually takes. And we passed. That's funny, I actually changed it before it loaded the file. 224.15.4786.383. Okay. Let's take out these and just make sure that it passes the test from before. Okay, that is beautiful. So that is the Hartree-Fock procedure. Yeah, we haven't computed the... We have not computed the integrals ourselves. We definitely didn't compute the geometries ourselves. But that is the Hartree-Fock procedure. So really, once you can slot your own integrals in there, there you go. That's pretty cool. Okay. Wait, what? This is my last commit. Iterate and get the final. Okay. Add the other test cases. That's great. I'm very impressed we didn't have to change anything. I guess the last thing I'd like to do is maybe move these to a separate file. Just move the test to a separate file. We'll call it HF tests. Let's see if this still runs. Yeah. What is this? Can you do this? I kind of imagine you can't do this. Alright, fine, make it public. Okay, compiled. I'm gonna get a warning for that. Okay, great. Yeah, so I guess that's going to be it. Thanks again to everybody who came by. Oh, it was a lot of fun to live stream. I hope you guys enjoyed it too. Yeah, I think that's it. I've said enough times what the future of the project looks like. The one thing I don't know, and I'll probably have to investigate this off stream a little bit, is how exactly live-in works. Maybe I'll do a stream just looking through it, trying to figure out what's going on. Yeah, because this is really going to be the future of the project. This is what I'm really excited for. This part today, I mean, it took 3.5 hours, so it's a fairly significant amount of work, but I think it pales in comparison to what this will be, because this is really the exciting part, doing the integrals myself. Integrals, basis sets, stuff like that. That's what I'm excited for. I found this great paper that talks about implementing semi-empirical methods. So, I think once I have some of the integral stuff, semi-empirical methods will also be another thing on the table. Anyway, thanks again for watching, and I will see you all next time.